Hello class. Today we're going to cover Chapter 9 on earthquakes. So earthquakes are said to be the most inevitable geologic hazard that there is. In the coming lecture, we'll cover what earthquakes are, the study of earthquake waves or seismic waves, how we can locate the source of an earthquake, determine the size of an earthquake, both in intensity and in magnitude, the destruction that they usually cause and the secondary hazards that they bring, where they typically occur, and the forecasting of earthquakes, as well as a little bit on seismic waves and what they have to do with the interior of the Earth's structure. So, ground shaking caused by the sudden and rapid movement of one block of rock slipping past another along fractures in the Earth's crust is what earthquakes are. In this case, where an earthquake occurs is going to be that zone, that fracture, that fault, if you would. So the energy that was stored within the fault, the energy that was building up due to the stresses being applied, is now released through a sudden and rapid movement, which is what an earthquake is. The fractures within the Earth's crust at which the slippage of the two blocks occurs are called faults. Okay, the fractures that typically are some sort of plane, they're called faults. They're usually locked, meaning that they are unmoving due to the confining pressure from the surrounding rocks. And again, remember that confining pressure is pressure that is equal in all directions versus differential stress when you have more pressure in one direction than in others. So the confining pressure that is typically being exerted will, for the most part, will keep the fractures locked by squeezing them shut in all directions until there is enough stress applied in one direction. There is some sort of movement in which this stress in one direction is going to initiate movement along the fault. So this movement is what an earthquake is overall, and thus it will typically occur in some sort of pre-existing fault, some sort of weakness plane that already existed. So these are already, again, points or planes of weakness that are typically pre-existing fractures from a previous earthquake, from a previous movement. So the exact location along the fault where the slippage begins is called the focus or the hypocenter. So this is going to be this location where the slippage is going to start. And the seismic waves, as you're seeing, and we will look at in further detail later, will radiate outwards from that focus or hypocenter point. The point at the surface that lies directly above the hypocenter is called the epicenter. So you're seeing the epicenter is usually what we refer to as the location of an earthquake, is the point that is directly above the focus or the hypocenter at the surface. Okay, so the energy that is released from earthquakes is perceived as seismic waves. And these are a form of energy that travels through the lithosphere and the Earth's interior, and that will later radiate outwards from the focus. So again, remember, this is the focus. Seismic waves radiate outwards from the focus out into further places, depending on how far or how they travel, and we'll look at that later. So although seismic energy dissipates rapidly as it moves away from the source of an earthquake, so as it moves away from the focus, some instruments that have high sensitivity can usually detect earthquakes. So they can detect this shaking. And these can do it even when they occur in opposite sides of the Earth, which is amazing. And again, we'll see that later within the lecture as well. So usually there are thousands of earthquakes daily within the world, actually, but thankfully only about 15 every year are large enough to be recorded as large, if you were, And these large earthquakes tend to be of magnitude 7 or higher. And these magnitudes will make more sense later when we cover them. So some of these actually happen in remote locations, some of these 15 or so per year. So even though they might be very, very large earthquakes, there's no population, no populated areas near where they occur. And so it's basically as if though they didn't happen to us humans. But of course they have. So for those large earthquakes that occur in heavily populated areas, however, the damages tend to be very catastrophic. Typically, they impact the infrastructure of buildings, of roads. They rupture gas and power lines. Sometimes by doing this, they cause fires, and not to mention, obviously, the loss of life that occurs due to all of these secondary effects. So there are two examples here within the slide that I listed. The first one is from the Mexico City earthquake of September in 2017. This earthquake was of magnitude 7.1. The damage to some of the city buildings was very high, as you can see in the top two pictures over here. The second earthquake that I have listed here is the Nepal earthquake that was a little bit north of Kathmandu in 2015. This earthquake had a magnitude of 7.8. And also due to the poor construction and the location of many of the houses and buildings, many of them actually turned into a pile of rubble, basically, as you're seeing right here. So this picture is a before and after of this building, and this is just the location of some houses or apartment settings as we're seeing. A very good place to follow seismic activity is through the USGS website on earthquakes. So give me 1 second. So let's follow that. Okay. So this is that specific site. You can just look it up on just the USGS earthquakes and you'll be able to see this. But you're able to see the different earthquakes that have happened in the past 2 or 3 days. So for example, this one of magnitude 5.1, which is relatively large but not huge, happened over here in the pretty much the Philippines area. Let's see any other big ones that we can find. Fairly large one in Indonesia. There was another one in Guatemala not too far from here, I guess, that was also kind of large. And then another big one in Alaska, which happened again this morning, or this afternoon. So you can see there are a lot of earthquakes. Some of them are a little bit bigger, some of them are a little smaller. In this case, I'm not finding anything larger than 5.5 magnitude or so. But as you're seeing the map itself, you're seeing that there is definitely a lot of seismicity, especially around this area of the Pacific. Again, covers this area right here. So definitely if you're curious about what is going on in terms of seismic activity in the past few hours or days, go to the USGS website. They have very good resources on earthquakes. They don't just tell you what the earthquake was. So for example, let's take this one in New Zealand. We can click on that specific one. It tells us not just the magnitude of it, tells us the distance from the island. It tells us some regional information about the seismicity of the area. It tells us the intensity reports. In this case, there are no responses to did you feel it reports. It tells us a few more things. So you guys are definitely welcome to look at this site. I encourage you to do so. It's a very good resource. Okay, so earthquakes can occur by a variety of things, such as volcanic eruptions, like we saw in Chapter 5. They can also occur due to massive landslides, due to meteorite impacts. But usually these tend to cause relatively small earthquakes. Larger and more destructive earthquakes tend to occur by Earth's movements. So, as we have seen thus far in this class, the Earth is not static. It doesn't stay or have the same processes, or not even processes, just simply have the same conditions. But it is rather very dynamic and changing. So we know that some parts of the Earth move upwards, for example. Examples of these are Mount Bora, which is in the Lost River Range and is the highest peak in Idaho. But also places where, for example, we have peaks made out of fossiliferous limestone. So fossiliferous limestone, if you remember, is made up of marine fossils, so meaning organisms that make up the rocks that used to be at sea level. And these rocks have now been uplifted thousands of meters above sea level. So we know that they have definitely been uplifted, moved upwards, vertically speaking. We also know that certain parts of the Earth have actually moved downwards, like the area in the Death Valley in California, for example, which has exhibited extensive ground subsidence or subsidence. And we also know that there is not just movement restricted to that vertical motion, so things don't just move up or down, but they can also move horizontally, which creates offsets of, for example, fences, roads, river courses, etc. So there is movement of the Earth, not just up and down, but also sideways, and also sometimes a combination of both of them. So an example of this sideways movement that we have is the area in San Andreas Fault, which is in California, for example. And we'll look at it in a little bit more detail in the next few slides. So overall, the actual mechanism of earthquake generation was unknown until H.F. Reed conducted a study following the 1906 San Francisco earthquake, which was so devastating that Reed felt compelled to do something about this. So Reed noticed that the horizontal surface displacement that came along with the 1906 earthquake, that displacement was of many meters along that northern portion of the San Andreas Fault. So this displacement in certain parts was as large as 9.6 meters, which is about 30-some feet, 32, 33 feet, something like that. So very large displacement, horizontally speaking. So after Reed did these investigations, he concluded that over tens to hundreds of years, differential stress will slowly bend the crustal rocks on both sides of a fault. So this is much like, for example, a person that is bending a wooden stick, like you're seeing over here. Over here. So usually there's going to be some sort of bending, obviously that is ongoing. There's going to be some frictional resistance, as it's called. So that occurs right here, frictional resistance right here. Once that frictional resistance is exceeded, then there's going to be some slipping occurring at the fault, and that is going to produce the earthquake, that slippage. Okay. So at some point, again, that stress is so great that it overcomes the frictional resistance, that locking mechanism at the fault. And that is when we get the earthquake. So the deformed rock will return to its original shape, which is right here, relatively speaking. This is the original shape in the one side. This is the original shape in another side. This original shape, if you would, is stress-free right after the moment of slippage. But it will start building up again. So the stress will start building up again soon after the slipping begins. So it's kind of a cycle. So you have basically original position, no stress yet. You start to have some stress in which you have that frictional resistance avoiding the fault to slip. Then you have the slippage, and then you have back to original position or so. So the springing or the snapping back into the original shape that occurs at this point was termed elastic rebound. Okay, so that's an important term. So the elastic rebound was named in such a way because the rock blocks behave elastically when they are released, when the energy is released.